yeah, no, that makes sense. Well, I think the way that the person that all the classes you fit in, you don't have to do everything that you should. Yeah, but if you make the count total credits, only do this, but if it's 4 years, that's total credits, that's what this now. They don't.
Well, I think we can get going. Welcome back, everyone. So today's class, it's going to be all about section 11.10, that Taylor and Maclaurin series. We have done one Maclaurin series already. We're going to look into a couple more, and then we'll look into a couple also Taylor series. Some of these will be a little bit trickier, but some of them will be pretty routine. And once we get through this section, we'll be looking into this section, part 2. This one has just interesting computations that you can now do once power series are on the table. So the extra things that or could be considered applications in the same section. But this is going to depend on how far we get in here is going to depend on just how many questions we might have on our exam 3. So our exam 3 information we discussed on Monday is listed out here. And you're always welcome when we come back on Thursday's class to ask any question relative to this material. Out of any document, any section, or any just question you have relative to this, we'll make sure to take them all to start off class. And like we mentioned, if it turns into just an impromptu review day, it's probably time well spent. So that's our plan so far for the rest of the week. Any questions at all, folks, before we get started with today's work? Okay, first we should probably try to decide or try to resolve in our minds, what are we doing in this section? That's always the toughest part about all of this. We're finding a Maclaurin series for F. What that means is we want to rewrite e to the x as a type of power series where the center is directly at 0. And the fact that it's a Maclaurin series is also captured right here, that we're going to use the coefficients by this formula when we go to represent it. So this is what it means to have a Maclaurin series altogether. It's a specific kind of power series. And the way we developed the formula for it was, all you do is you write down the power series. You then expand it. So starting at index 0, index 1, and so on. Upon expanding it all, you can get the first coefficient. Just evaluate f at a. All that stuff gets deleted. F at a is C0. You differentiate the last line up here, and you get a new line, and just repeat the same exact trick. F prime at a now gives you the value C1, and so on down the line. We established a pattern. We then started solving for the coefficient C0 from the prior equations. And when we solved them, we noticed a pattern really does emerge. This is basically the same exact steps of doing any power series. We differentiate, we do an evaluation, and we try to get a pattern on the right part. So what the pattern was telling us, these parts highlighted in yellow, is that for all n greater than or equal to 0, if C4 is the 4th order derivative at the center A divided by 4 factorial, and we expect this pattern to continue, it really does, then for all n, the nth derivative of n at the center A divided by n factorial is the coefficients of that power series. So all that information just gets plugged right back over here. Once we did that, this was just a put all the results in one page section so we don't jump through different sections multiple times. But putting it all together got us to that spot right there. If F has a power series representation at center A and radius of convergence R, we can write it in that format. This is the coefficients that we were solving on page 1 of the notes, times x minus a, where a is the center. And we have absolute convergence when x minus a is less than r. So very strong convergence, which means this is as good as a function representation as the left-hand side might have been. So that's how we developed the definition for the Taylor series or Maclaurin series. Any questions about getting down to that formula there? Okay, then once we have the formula, this is us essentially just redoing exactly what we did on page 1. We take a function, we put in the center, we get a coefficient value out, 1, Really, we're just looking at the numerator for Cn rather. We differentiate, we evaluate f at the center, we get a value 1 again, and we want a pattern on the right column here. We observe that any order derivative we pick, because the nth order derivative is always e to the x, e to the 0 is always 1, it provided us this formula. And this formula now holds for all n greater than or equal to 2. Didn't really have to emphasize that, or greater than or equal to 1, or hang on, greater than or equal to 0 is where the indexing starts. Maybe it's a good thing we wrote it down. Just a reminder, indexing really starts here. This is the index n is 0, n is 1 for first derivative, n is 2 for second derivative, and so on. So we found it out, it's always 1. Formula for Cn just divides by n factorial. So we threw n factorial, here's x minus 0, 0 being the center, simplifies to just x power of n. And that's our Maclaurin series for e to the x. Really kind of weird in a way, right? We look at this really, really carefully. Here's another view of what we just did. Here's the function on the left-hand side, e to the x. Our standard exponential function, but now it's being represented this way, x power of n over n factorial. These things are really abstract just to look at. So if we're going to put that in a calculator, you might want to go through the mental exercise of just expanding it. When n is 0, we're going to get just a 1. When n is 1, we get x. N is 2, we get x squared over 2. At 3, we get x cubed over, we might as well use factorials now, 3 factorial, and so on. So we can't put in infinitely many terms, so that plus dot will go away eventually. But let's put in the terms and see what we get. You have to write this as a function. So f of x equals 1. So terrible approximation so far, right? That doesn't do a good job. Plus x on this one. Curiously, this is a good approximation. Only if you're right here. This is the best local linear approximation of e to the x at the value center 0. And it does a really good job. As long as you're, say, within maybe 100 on either direction, the difference between 1 plus x and e to the x is very, very minimal. And this was a discussion that we were having earlier in class. Like we mentioned, this is the best local linear approximation of f at the center 0. And it's something you do in Calculus 1. In Calculus 1, you do a linearization process where you take a function that's differentiable, and linearizing it means you write this thing down. This is just the tangent line equation. Solve it for f of x, or rewrite it as L of x as a full-on linearization. It's f at a plus f prime of a times x minus a. And that's inherited directly from these expanded terms on page 1.
You know, if you put like this, am I making this up?
Local linear approximation is just those very first terms right there. Then the power series gives us more information. It gives us the quadratic approximation. We add 3 terms, we have the best local quadratic approximation to e to the x. Or we could go to the cubic or power 4 and so on. So that's what this is really all about. We're just extending what is a powerful tool down there, but it has limited value because the convergence for e to the x is, well, not convergence, but really the accuracy for e to the x only really works great around 0. So if you need to be, say, further than 0, maybe within negative 0.5 to positive 0.5, somewhere from there and there, we see a problem with the function, right? There's some decent separation. That might be error we can't tolerate in a system, wherever we're doing. So we go to the best local linear quadratic approximation, plus x squared, divide by 2, and we can see that did a way better job. Well, a little bit of difference over here, maybe, if that's important. Then we go to the cubic term, x cubed over 3 factorial. And now it looks like in this range, we have an excellent approximation. Zoom out, though, and you start to see the problems. It doesn't work forever, right? we can't put in infinitely many terms to make this accurate for all real numbers. The trouble with our approximation on this one was we centered it at 0. And that might be okay if we want to calculate, say, f at maybe 0.1. We calculate f at 0.1. This is a great approximation because e to the power 0.1 matches it really, really well up to that digit. And we only used 4 terms in our approximation. The convergence here is just shockingly fast on this kind of thing. But if you wanted e to the power, say, maybe -10, somewhere out here, we're expecting close to 0, and we go f at -10, we're way, way off, right? There's a fix, but there's 2 fixes. One fix is keep on adding more terms. X power 4 over 4 factorial. Hey, that helped. We're getting kind of close to that value, but it's got to be at 0. Add more terms, plus x power 5 over 5 factorial. And that one didn't help as much, but let's add just one more and we'll end this exhaustive search for good accuracy. X power 6 over 6 factorial. The evens seem to do a better job, but it doesn't seem to be converging too well. If I put in infinitely many terms, it might, but you know what the problem really is? If you want to approximate e power -10, the center is wrong. The center should be closer to somewhere out here where you're trying to do the approximation. Our approximations are great with finite terms, only nearby that center. So f-1 and e power -1 match up really, really well. But if we go too far out, it starts to mismatch on us quite a bit. So that's in essence what's going on every time we find a power series representation. We're finding great ways to approximate. I think we've mentioned this before as well. What is Desmos doing then to do this kind of approximation? Well, behind the scenes here in this web browser application are methods just like this. It's really just taking the function, finding the right center nearby -1, whereas accurate information, doing an approximation, deciding how many terms it really needs for high enough accuracy, and it just does it all blindly fast. It's a computer after all. We're doing it the slow process way by just discovering what was the Maclaurin series in the very first place. So that's kind of like a 13-minute review of what we did last class, but it's a slippery topic to know what we're even calculated. Any questions about what we're looking at into so far? Okay, our goal next is practice this further. So here's our next one. Hyperbolic sine at x. This is a part B, so we're doing the same thing. We're looking into a Maclaurin series representation of that thing. And maybe before we even get started, it might have been a while since we looked into hyperbolics. I think we did it once in this class, maybe chapter 8. It's hard to remember. So let's redefine it here just for easy reference. Hyperbolic sine at x is e to the x, sine in the middle, e negative x. Anyone happen to remember what is in the middle? Is it plus or minus? Good call, absolutely. It's a minus in the middle. And then we're going to need hyperbolic cosine as well. Hyperbolic cosine at x is e to the x just plus right there, and then everything else is the same. So with those 2 definitions down, we're ready to do the Maclaurin series. So we want a Maclaurin. I'm not sure if I remember how to spell Maclaurin. Let's just go with that. I'll revise it if necessary. We want the Maclaurin series for hyperbolic sine x, and that just means center is a equals 0 on this problem as well. Next one was going to be a Taylor series. So to start off the process, it's a 2-column system. That's a good idea to spend some time here because we're trying to find a pattern. And the faster we go, the more invisible that pattern is going to be. So methodically, write down the 2-column system, f on the left, f at the center on the right. So it's f of 0, which is hyperbolic sine of 0, That's just a 1 minus 1 in the numerator divided by 2. So it outputs a 0 on that evaluation. Now we're producing several rows on this one. The derivative of f at x is hyperbolic cosine. Now the derivative of f at the center means we're passing 0 to the hyperbolic cosine. Either the 0 is 1, so it's just 1 plus 1 in the numerator, 2 divided by 2, and we get a value of 1 altogether. Then now this is the rinse and repeat stage. We might go a little bit faster here at the moment. F double prime at x is hyperbolic sine at x, which means at the center 0, f double prime is 0. Then the third order derivative at x is back to hyperbolic cosine. So that means the third order derivative at the center 0, 1 again. Here's where you have to make a judgment call. For a lot of people, this might be enough. For me, I think I'd probably want at least 2 more to really see the pattern, because this problem is tricky. Notice all the zeros in here. We don't want a power series with half the term 0. That would be something we want to simplify. We need to put in the simplified expression, which means we're going to have to re-index this whole list right here. So another set of rows might be a good call for re-indexing, throwing away half the information that you see. So let's go fourth order derivative. It's just alternating between hyperbolic sine and hyperbolic cosine in the left-hand column. So over here at the center 0, we get 0 again. And this will be the last one, fifth order derivative. F parenthesis 5 means f prime, 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 prime. So that's a better way to say it. Is cosh x. So fifth order derivative at 0. Because it's a hyperbolic cosine, we're back to a 1. So that's what the list looks like. It's a weird looking list. So here's what the strategy ought to be whenever this happens. Let's track our indexes. We're going to re-index them, but the indices are so far n is 0, 1, 2, 3, 4, and 5. Now we need to make another kind of observation. It turns out, and let's start maybe with even. An even number always has the form 2n for some integer n. So for example, if I plug 0 inside there, I'd be getting 0. If I plug in an index 1 inside here, I would be getting 2. If we plug in an index 3 or 2 in there, I would get the index 4 and so on. So this is the form of any even number whatsoever. Plug in an integer and it'll take you to all the even indices where the values come out as 0 altogether. The evens are 0 is essentially what this is saying. So if we write f to the 2n at the center 0, this is always 0, no matter what. That's really good information for us. And now let's go to odds. Any odd number is of the form, take the even expression, and you hit an odd the minute you add 1. Let's practice with that one. This is just scratch work, so I'll delete this in a moment. If n is 1, 2n plus 1 becomes a value 3, but let me start with 0. Thank you on that. You usually want to start at indexing 0 for Taylor series, Maclaurin series, just power series in general. If n is 0, we get an index 1, our first odd. If n is 1, we get an index of 3. That's our second odd. And so on down the line. If n is 2, we're going to get the index 5, our third odd down the line. These are the non-zero ones. These are going to be the ones we don't delete. And notice I have double meaning on indexes. I'm writing down n here because I'm thinking the formula 2n plus 1. I'm getting these values as indices, ignoring the n equals 1, 2, and 3, just going down the line to where we see these values. So that's a scratch work for seeing what this is trying to say, 2n plus 1. But now we can say f at any odd index. or let me say this better. At the f at an odd order derivative at the center 0 is always 1, no matter what. So that's the non-zero values. We can now say next, C2n. Let's say where that's coming from before we write it in completely. C2n is coming from this part, or Cn in general. So from right here, that's the coefficients. And we call it Cn. What we're doing is trying to find the numerator first of Cn, because then we just divide by n factorial. But if we're indexing at the Indians 2n, we're talking about C at 2n. C at 2n is going to be 0 divided by, not n factorial, we use the index that we stated. It's divided by 2n factorial. That's always a 0 no matter what. So we're going to delete the 0 values, only keep the non-zero values. So on the right, here's the non-zero stuff. C at 2n plus 1. Coefficient at odd indices is what this is saying. We'll take in the derivative at 2n plus 1 in the numerator. That's just a 1. And then it will divide by 2n plus 1 factorial. So that's what's going to go inside right here, except we now have to call it C2n plus 1, which means the power right here on x is also a 2n plus 1, and we'll have a 2n plus 1 factorial in the denominator. Really, really touchy whenever you have half your term 0. So this problem is kind of a warm-up problem for when you do a problem like this for sine, and when we do a problem like this one for cosine in the end of the document. Okay, here's the next stage of the process. This suggests re-index. We're deleting the 0 terms essentially. So re-indexing means we want that out of there, that and that gone, and so on down the line. Writing it lightly because it was important. It's what established the pattern for us. That index is right. N equals 1. This index is wrong. This is now n equals, hang on, that index wasn't right either. Let me start over. Recall we always start our indexing right at 0. That index is not right either. This will be n is 0. Let's point also this way to say we're re-indexing over here as well. Then we have a deletion. This one we re-index to a 1 rather. A deletion. And then this one's re-indexed to a 2. And then take a look at the indices. Plug 0 inside here, and you would get, let's maybe look at the derivative. Plug 0 inside here, that would just be f prime. There's just a 1 left over. So you're talking about f prime here for a 1. Plug a 1 inside here, you're talking about f triple prime, which is this one, taking us to the right value. Plug a 2 inside, we're thinking our new index when we say plug in 2. Plug in 2 inside, and that would be the value 5, fifth order derivative, giving us the right value again for a 1. So the re-indexing is really pretty tricky. This is a good spot to pause on. So we deleted everything that had zeros. We looked into the non-zero stuff, and then to start off going by 0, 1, 2 on all of that non-zero stuff. Critically, if you put 2n plus 1 here, you have to have Cn 2n plus 1 here, and 2n plus 1 factorial. Those are the easy, small things that could be forgotten. Any questions at all, folks, on this re-indexing phase before we go and put it all together? Okay, here is the let's put it together step. Our whole goal is to write down something for hyperbolic sine of x. But now we have some really good information. Hyperbolic sine of x can be rewritten as pretty much that. We have all the information we need. In place of Cn, we're plugging this expression in. Let me scroll down a bit. So this is going to be a sum going from 0 to infinity using these indices. You know, we can emphasize that a little bit better. Let's do it this way. starting at 0 for infinity, with the re-indexed list, we're going to begin by going that structure placed in 1 over 2n plus 1 factorial. Then it's multiplied by x minus 0, since 0 is the center, but that simplifies to just x power n. However, it's not power n, it's power 2n plus 1. There's a matchup with the factorial, as well as the power on x itself. So if we're only giving odd terms, we're only getting odd powers on x that was assigned to those non-zero odd terms. We got it, folks. That's the hardest bit about all this. Re-indexing when you have half your list 0. And it takes us right to this expression. Let me rewrite it just slightly more compactly. N goes from 0 to infinity of x power 2n plus 1 divided by 2n plus 1 factorial. This almost looks like the power series expression for sine itself. The only thing it's missing is the alternating part. Sine and cosine as a power series, Maclaurin series, or Taylor series will have -1 to a power. But the rest of the stuff is really dead on. It's kind of remarkable. We need to do one more thing. Example 1, now in part B, wanted a couple things. It wanted the power series representation, there it is, and it also wants the radius of convergence. So we're going to find the domain upon which this is a valid approximation. So let's give that a try next. Really, on the last step, all you're doing is another ratio test. It goes like this. We've used this test quite a lot, but these things can get pretty built up now that we're dealing with Taylor series and Maclaurin series. So it's a good idea to do this really methodically. AN is going to be x. Well, let's do this really methodically by recalling the hardest thing is AN plus 1. Let's start with that one, the successor term after AN. AN plus 1 is going to be where the red dot is. Look into x to the power 2, n plus 1 divide by 2, n plus 1 factorial, written out in that specific way. So just doing this one carefully, all I've done is substituted in n plus 1 for n. It now simplifies to x to the power 2n plus 3 up into the numerator. And likewise, there's a lot of parallelism here down in the denominator. 2n plus 3 factorial as well, when we simplify and combine. And because we're going to divide by this term, it tells us how we should simplify. We could do this on the step down below, but let's do it on this line. I want to cancel x power 2n plus 1 into 2n plus 3. That suggests we should factor out x squared and leave x to the power 2n plus 1. We also want to cancel 2n plus 1 factorial into 2n plus 3 factorial. So this should factor until we get to the 2n plus 1 factorial part. So 2n plus 3. Descend by 1, 2n plus 2. Descend by 1 again, 2n plus 1. But that's as far down as we need to go. So now we put in the factorial. Other thing we did with the ratio test is we called the whole thing up here summation AN. And we're allowing AN to be just that. So we're ready to run the test. Those are the two major components. We now need to take a ratio of them. I guess the test is well named, right? Go limit. N goes to infinity of AN plus 1 divide by AN. This then turns into the limit as we go to infinity of just directly copy in all this information carefully. There's a lot of stuff. I have the particular habit of just miscopying something or forgetting to copy it at all. So there's the numerator, 2n plus 3, 2n plus 2, 2n plus 1 factorial down below. So that's the first portion in. Test indicates we divide by an. So we flip this entire fraction. Not sure what symbol that was supposed to be. Let me rewrite that. Take 2n plus 1 factorial divide by x power 2n plus 1. And this kicks off the ratio test. We always expect huge cancellations. And that's the biggest one. It completely just nullifies the factorial. That's why this would have been hard to test otherwise. X power 2n plus 1 is also completely gone. And now absolute value serves no function because x squared is also positive, and the values of n we're assuming positive per that limit. So this is now just x squared, a limit as n goes to infinity, 1 over 2n plus 3, times 2n plus 2. It's good to get it all in there accurately, but the whole limit is 0, right? It goes to 0 really quickly. It's quadratic in the denominator. So this is equal to x squared times 0. Now the whole limit is 0 despite however large x tries to be. We just get a 0 there. Less than 1 in the ratio test implies absolute convergence. But this happened for all x. In the real number system, feels like it's good to define that here because we use R as well for the real numbers, but that's a special R symbol to say the system of real numbers. And then finally, that gives us our conclusion. We can say, therefore, hyperbolic sine of x, if we ever needed to, could be re-expressed as a summation from 0 to infinity, x power 2n plus 1, 2n plus 1 factorial, with radius of convergence infinity. So this R is different from the one above. It's just expressing any value of x is going to work for absolute convergence on this expression. So we got it, folks. That's our hyperbolic sine as now in Maclaurin series. Any questions at all on getting this computation to work? Okay, it's honestly a really rough problem. Not because of this part right here. Once you have this information, everything else kind of flows in the same sort of way. This is the hard part. Getting this list written out and then re-indexed based off even values and odd values, it's something that does require practice. It's kind of a weird problem. And we'll come back to it on this one right here, cosine x. I think I had one more problem. I forgot about this one, 5 power x. We'll do that as our next one. Still doing the Maclaurin series. Let me just re-screenshot that actually. So here's our part C coming in next. So it's a little bit different, 5 power of x. It has a kind of a messy derivative. We did e power of x, so we're kind of extending on that one there. So first problem was e power of x, which is really easy to see the pattern. The second one had a nice pattern, but only for the odds. So the purpose of example 2, or part B of this example, was about reindexing. And now the purpose with the part C is the derivative is just messy, so we have to be really careful as we go. So like before, just as a reminder, center equals A, which is 0, since we are providing a Maclaurin series. So that means when we go to start this off, we'll begin with f of x is 5 power of x. And then immediately just go f at 0, but let me put in some space. Like I said, the derivative is a little bit messy on this one. F at 0 is 5 to the power of 0, which is just a 1. Okay, there's our center just being re-expressed as going into that part. Now we go to take derivatives. But if you forgot this derivative, I would totally understand. It feels like it just doesn't come up a lot, which is really weird. Depending on your instructor, it may have came up not much in Calculus 1 even. Anyone happen to remember the derivative to 5 power x? Yeah, exactly. We do the natural log 5 for the full derivative on this one. And the thought with that is, it's the same with e to the power of x, except e to the power of x, natural log e, gives you just an unnecessary factor. Natural log e is 1. It doesn't simplify in this context. We have to really write it in. But then we do f prime at 0 on the right-hand column. 5 power 0 is still a 1. But now we have something interesting. Natural log 5 is going to have to be part of our pattern here. So here's natural logarithm of 5, and then we're just going to continue down the line. If we take the second derivative, we'll have 5 power of x again, then natural log 5 times natural log 5. The power on that factor is just going to go up by 1. So 5 power of x, natural log 5 squared on the second order derivative. That means the second derivative at 0 is just natural log 5 squared. 5 power 0 still goes to a 1. This is starting to exhibit a pattern. Let's just maybe do one more derivative. We did do the fifth order derivative on the last problem, but I think the third order derivative should do it for us. Third derivative of f at x is 5 power of x times natural log 5 squared times natural log 5 again from the original derivative on 5 power of x. So we just get natural log 5 cubed this time. So third order derivative at the center 0 is natural log 5 power 3. There's pretty much a pattern looking at us right here. But before we guess the pattern, we should see if we can complete it by hand. Here's what I mean by that. Let's see if we can write down third order derivative in this kind of format for all values. So this is, I guess we don't have to recopy that. That'd be kind of weird. But over here, we could put in power 1 on that. Natural log 5 power 1 is just natural log 5. We really want to see the power 1 because it matches up with the first derivative here. Now this is the function value, and in our notation, we think of this as the 0th order derivative, as weird as it sounds. We get a 1, but you know, 1 is natural log 5 to power 0, matching up with the 0 order derivative. So our indices would go n is 0, natural log 5, 0, n is 1, natural log 5 power 1, and so on down the line with our indices. If we can make this pattern really get forced into working, then here's our conclusion. This whole table tells us immediately, without any further struggle, any further reindexing, that the nth order derivative of f at the center 0 is natural log 5 at power n, because we're always matching the order derivative with the power on natural log 5. So this pattern holds for all n greater than or equal to 0 being integers. So then it tells us the immediate next step is that the coefficients for this Maclaurin series, defined as Cn, are going to be Fn at the center divided by n factorial. So in this problem, it's natural log 5 power of n divided by n factorial. So this is the sequence of steps. Build out your 2-column system, find the pattern for the nth order derivative, and once you find the pattern, whether you call this Cn or not, you're going to do the same step. Divide by n factorial and plug it back in down here. We're just going to multiply by x power n now to complete the work on this one. So this one's definitely a break after the last one we got through, hyperbolic sine. Let's take a moment. Any questions at all, folks, to this step? Okay, so here's our next step then. With theorem 7 in view, we'll say that 5 power of x, the original function we want to work with, is now a sum from 0 to infinity of all that stuff, just gets imported in, natural log 5 power of n, divide by now n factorial, and then take whatever you have, go x minus the center to the power of n, which is always a weird thing to say with the Maclaurin series, but we're about to do the Taylor series, so that's the right thought to have every time. It's always x minus the center, but if the center were 0, you get to put in just x power n for short. plugging it into the numerator just to make the ratio test feel a little bit more streamlined, but you could offset it outside the fraction if you preferred. So that part's done. One pattern you might have noticed that we've hinted at a little bit in the, I think, section 11.6 maybe, is that when you see an n factorial down below here, it's really kind of giving you a big hint. The radius is probably infinity, almost a guarantee, unless something over here involves a factorial or is growing at a rate faster than a factorial. So if you did this right here, r equals 1 infinity, then I would just think of it as you have noticed a different kind of pattern. Factorial implies the radius. We still have to show the step though, so this is a bit of the annoying part. We still need to run through the test, but no harm of just putting down on paper your expectation if you feel really confident about it. I'm going to put a box here to convey this is the answer, but we still have more work to do down below. Here's that work. Ratio test. Let's do the same exact pattern because now it is really a pattern and a routine to run through this test. And that's how you kind of want to study these tests. Do it the same exact way each time, make it methodical, and then it's just going to feel like muscle memory when you do it in an exam setting. So an plus 1, it's replacing all values n with n plus 1. So it's natural log 5, n plus 1, x power n plus 1, n plus 1 factorial down the denominator. This problem is not as built up, so we'll do the simplification on the next step in the limit. But let me also write in an natural log 5 power of n, x power of n over n factorial. Did it slightly different. I didn't want to write equal summation an here. I want this to be just the end answer. So now take the limit as n goes to infinity. Every time I wrote down the ratio test, except this time, essentially every single time I did this. This is just the reminder of how the ratio test goes, and it's still a great strategy for studying. Write down these structures, because if you write that down every time, you're going to notice you've just memorized it without ever having to really try to intentionally study it with flashcards. The more you write these things down, it's just snaking its way into your subconscious. It's building a neural pathway. You'll write this almost automatically. And if you're low on time and you just want to write it down now, we know based off what we've been writing down all along in this class, it's this one first. So let's put it in. Natural log 5 times natural log 5 power n. I'm factoring it down as I go as well. Times x power of n. And I want to cancel n factorial into n plus 1 factorial. So our standard trick is write in n plus 1 times n factorial there. Then we immediately go to multiply, not by that, but by its reciprocal. That actually kind of looks funny. I wanted to have a parenthesis there. So this is natural log 5 power of n, x power of n. Oh, I messed up. We're multiplying by the reciprocal, right? So let's flip that. One more try. Got to love Control Z on these things. N factorial divided by natural log 5 power of n, x power of n. And now we're on our way. So let's eliminate the factorials. Anything to power of n is also gone. It's kind of the nice thing about the ratio test. Huge cancellations every single time. Absolute value is going to settle right on here. Then, let's pull out even more. Natural log 5 is also a constant, just like absolute value of x is. So absolute value of x and natural log 5 are not indexed by n in the limit, so we can rewrite them this way. Factored out, only thing left behind is 1 over n plus 1. But this is probably like the 60th time we've done a limit like this. Who knows? We've done lots of these type of limits. Constant in the numerator, degree 0. Degree 1 polynomial in the denominator. As you go to infinity, that limit is just a guaranteed 0. So this turns into absolute value of x, natural log 5, times 0. It's 0 altogether. And it being less than 1 implies the absolute convergence in the ratio test. So we'll say this holds for all x and r, and implies the radius ordinary looking R is infinity, which we said on the onset because we saw the factorial, but this is kind of an annoying part. These problems can be really surprising. We're going to see one with the factorial below and above that simplifies. Radius is not infinity on that one. So this is a step we still have to show on homework as well as on exams. We must show this test. We'll see why when we get to the last problem on these notes. The very last problem is actually really challenging. It's going to stretch our pattern seeking abilities to the maximum for this kind of context. And the ratio test isn't either. The surprise will be radius of convergence is not infinity on the very last one. But this is the development for getting a 5 power of x Maclaurin series. It turns into this, and this is good for any value of x. We have great convergence. Any questions at all with that whole process? Okay. The best way to learn this kind of stuff is do a bunch of problems. So that's what we're going to do next. Here's our next version of this. But the example did change. This time, we're going for Taylor series as opposed to Maclaurin series. All those words sound really abstract, but all we're doing when we say Maclaurin series is we're saying the center is 0. The fact that now this time it's non-zero is the only thing that tells us it's a Taylor series this time. So right here, non-zero implies Taylor series right here. So we want to find the Taylor series representation of cosine this time. This is more challenging than hyperbolic sine, I'd say, but it's very similar in the reindexing step. And we're also doing it nearby pi. The reason we're doing that is, much like we were discussing with trying to get good approximations around -10, if we're dealing with, say, a cosine function, let's wipe out all this irrelevant stuff. But we want to do cosine right around, say, the value pi, roughly right around here. If we want values of, say, cosine 3, roughly around, exactly around here, then getting a good approximation of cosine 3 is tough if we centered our expression at 0 with the Maclaurin series. So if we want to calculate cosine 3, here's the value. What this calculator probably did was a Taylor series, and the value at pi is exact. It used an exact value, -1 for pi, to center the power series right here. So now we only need maybe 3 or 4 terms to get this level of accuracy in the calculator. This is another thing the calculator also does. Depending on your input, it tries to find the right center to output the minimal number of terms to get you this high degree of accuracy. And again, it does it extremely fast, even in the TI-83, which chips are like 30, 40 years old. So let's give this a try now. Taylor series development. It's the same kind of process, just a different center. So we'll have to be really careful how we write this out. Theorem 7 is no longer relevant to us. Let's go and grab, I guess it'd probably be theorem 6. Let's take a look. Yeah, theorem 6. So we're going to start analyzing it this way, now only because the center is non-zero. So let's drop that below. It's just our quick cheat sheet on how to get through the last phases. Now, next thing we do is same system, like with the Maclaurin series. Write out f of x on the left as cosine x. Then on the right, we're doing the derivatives. Excuse me, we're not doing the derivatives. Let me try again. On the right, we're evaluating at the centers. Not too sure what I was thinking there for the moment. So the center is going into the right-hand column, but f at pi is cosine pi, which is a -1. So we're starting at a non-zero value, but pi is an interesting thing to take because now if we take f prime of x, we're going to get negative sine x. And the first order derivative at pi is then 0. Sine at pi itself goes to 0. So this is now a little bit concerning. Half of the terms in our Taylor series is going to be zeroed out. We have to reindex, and we can already see that at this step. But let's keep going regardless. F double prime, derivative of negative sine x is negative cosine x. So F double prime at pi is not -1, it's negative of -1. We have something new in the pattern we're seeking. It's not a simple 1, 0, 1, 0, also alternating at the same time. So it's getting more and more built up as we go. Because this is alternating, and because the pattern looks like it's going to be difficult, I would say fifth order derivative at minimum is a good idea for this one. So let's keep on climbing higher. Derivative of negative cosine x is negative of negative sine x, so back to positives. So F triple prime at pi, 0 again, whether sine comes up as a positive or negative. Fourth order derivative is going to give us now cosine positive. We're back up at the start. This just keeps wrapping around, it looks like. So fourth order derivative at center pi is -1. And yeah, let's do maybe 5 terms. I have 3 non-zero terms. That should be enough for us to see a pattern. Let's just rewrite. Fifth order derivative at x, negative sine x. So now the fifth order derivative at the center pi, back to 0. So here's our list. It's always concerning when you see those zeros in there. There's more work to do now. Here's our next thought. Let's capture exactly how we analyzed this before. Writing in, let's say, evens is expressed as 2n. Odds is expressed as 2n plus 1. Let's put in our first index. The first indexing on this gives us n is 0, 1, 2, 3, 4, and 5. So when we say evens, those are the non-zero ones this time. The odds are the 0 ones. So this one goes a little bit different. So starting with 2n, every time we do f at 2n, we get a power of -1, either positive or negative. Let's put in -1 power n. That one's probably not quite right, because here's another thing we're doing. I need to delete this. Think of this as now scratch work on the margin. When we say evens is 2n, and we write f at 2n is -1 power of n, it also means we are reindexing. And the reindexing is going to start at a new index, different from these ones on the left, where n is 0 to start. When n is 0, we have the 0th order derivative, and the value here should be -1. Except -1 to power 0 is +1. It means we're off by a bit. We're not getting the -1 we expect. So reindexing, n is 0. After the 2n at pi, that should have said, let me see if I can fix that. F at 2n, don't forget we want to put in the center pi on that one as well, is going to become f at 0 at pi, which is just a complicated way to say f at pi, which is -1. Or excuse me, f at pi, yeah, that's -1 here, but then f at 0 in this formula would give us -1 power 0, which is +1. So there's our mismatch right there. On our list, when we reindex at 0 through f at 2n, we get the -1. But when we look at this formula, we're getting +1. Simple fix though, right? Add 1 and your job is done. Again, think of this as scratch work just to make sure we're on the right track. Let's do this one more with n is 1. So if n is 1, this part right here is going to give us f at 2n. So this is just second order derivative, f at 2 at pi. Then that would be -1 to the power 3 altogether. hang on. N is 1, yeah, so that would be power 3. Giving us a -1. I was not expecting that. Oh, I think I see my problem. So re-indexing at 1 meant I plugged a 1 right here, which means I do get a 2 right here. But N is still 1 right there, right? I tried to put a 2 there. That doesn't quite work. N is still a 1. So that's a +2, not a 3. -1 squared does come out as a +1. So this formula outputs a +1. And also when N is 1, we're going to be on the next non-zero term right here. We match up at +1. So this correction, -1 power N, then +1, was all we needed to get this to work out. So we're not quite done. This was just scratch work here for the moment. Does that make sense on the N+1 power? Okay, let me get this out of the way so it's not just like a cloud of thoughts and scratch work when we're to come back to these notes. Next thing we'll say, turning to the odd values, that's the N is 1, 3, and 5, and so on, is that F at 2n+1 at the center pi, it came out at 0 every single time. That's the 0 values we're seeing. And this is where we're going to re-index in earnest. It's because of that. Every odd value comes out as 0. We must re-index. So the re-indexing is going to then go over here. Maybe let's lose that arrow this time. So anything odd is going to be eliminated from the list. This is off the table. Or another way to say it, anything involving a 0 on the right-hand side is eliminated off the list. It's nice to see that matches up with the original odd indexes. Now we re-index only keeping the evens. This one's actually right this time. So indexing starts at 0 and 0 is considered even. That one's wrong. This index updates to N is 1. Then we just feed N is 1 right here. That's going to be F double prime, and F double prime at pi is 1. We also plug 1 in here, and -1 power 2 is what we get for the +1. So matching up like we expect. Then a deletion, a re-indexing on this one. This is N is 2, but we should always check these out. This is tricky enough as it is. When N is 2, we're coming over here, plugging in a 2. That would become, I'll write this in as scratch work, F4 at index 2. F4 at pi has to come out as, recall we're still at index 2, -1 to the power 3, which is a -1. And now let's check our list. Fourth order derivative at pi is exactly -1. So that validates our re-indexing really is working all the way down the line. Well, at least to the number of derivatives we indicated. We'll take that as strong numerical evidence. That's the right pattern. Next thing we might say is that over here, C, 2n+1, the coefficients of the entire power series, is 0 for all n. That's because the numerator is going to be 0 as well. However, on the left, C at 2n is going to be equal to F at 2n at the center pi. Then this divides by 2n factorial altogether. Let's rewrite this one more time. C at 2n, plug in the information. F at an even order derivative at the center is just -1 to a power. So this is -1 to specifically power n+1 to make our list work. Then divide by, let me just fix that exponent, that looked a little funny. Divide by 2n factorial. And now we are really close to the Taylor series representation of cosine at the center pi. All we need to do at this stage is plug in what's highlighted here in yellow. That part is C at 2n for this problem. So here's the big step. Take the original function. You can grab it here from the list or look up further, stated in part A. Grab the original function and rewrite cosine now. Cosine x Here's one thing that's kind of cool about these functions. In trigonometry and algebra, you're often talked about even functions versus odd functions. We get beaten into us in trigonometry that cosine is an even function because it's symmetric about the y-axis. But now we're going to see cosine as an even function because it's literally indexed by just the evens when we go to write out the power series. It involves just even powers, even factorials. So it's kind of a neat little tie-in with algebra there. There'll be a summation starting at a reindex n is 0. Just using that color to emphasize, we made a really big change on this list with all those deletions. Then we put in c at 2n, this whole thing, -1 power n plus 1, divide by 2n factorial. And we have to be really careful with this last step. This is a Taylor series with a non-zero center. So the center gets involved here as well. We don't do x power of n, we do x minus the center to the power of n. We look up the center just by going up to this spot. Center is pi. But let me see here. Let me match up the color coding a little bit better. Looks like we're using green to represent the center of power series, so we might as well keep that up. So that's how we get to the very end. I did make a mistake on here, though. The power's right, the factorial's right, but one other thing that has to happen is the factorial has to match the power right there on x minus pi to power of n. That has to be a 2n as well, right at that stage. So there's cosine x. We still need the radius of convergence on that thing. Darn it. But let's call our shot right here. I see just a factorial of the denominator. It's almost a guarantee infinity for radius of convergence. So that's a full set of steps on this one. Almost. We also have to, let's see here, find the associated radius of convergence. Means we need to use the ratio test on this thing one more time. But this is the tough work, getting to this step. Any questions at all, folks? Surviving to this stage? Okay. So last thing is going to be hit this with a ratio test. Let's get that out of the way for the moment. Part B is going to be like the challenge question. This one has a pretty tough pattern to spot. But if you're into challenges like that, give it a try before class, and we'll see if we can match it up. Now, next thing I'm noticing is I'm attempting a ratio test in 4 minutes with something that is a little bit built up on this one. This might be a good one to come back to. How do folks feel about that? Should we race through it or come back to this next class? Okay, that might be a kind thing to do. It's a tough test to use a ratio test, especially when you feel like you have a new context. This test is going to look the same, but x minus pi to power 2n, it really makes it feel more abstract than it really is. This is going to be a reminder to me since I notice I actually forget to come back to these. So come back because we need the ratio test. That's going to be a pretty strong reminder, I think. Well, we'll end class here at this spot. When we come back, the comeback to this is going to be after we take any review questions that folks might have on exam 3. So it could be possibly after we return from the third exam, a week away from today. But we'll definitely come back here, finalize the ratio test, and do the challenge problem down below as well. Well, have a great night, folks. We're ending a few minutes early since racing through this stuff doesn't help out anybody. I'm pretty sure about that. But come prepared with questions on exam 3 next time, and I'll be very happy to help out. Have a great night, folks. That's a good question. 4 for this one. And that tells you, which is interesting, radius of convergence is probably 4, because that's going to be the distance to a discontinuity at x minus 4.
So I'm not gonna be here for the test on Monday. Is there any way I can like, do it at the testing center on Wednesday?
Yeah, I can make that happen. Forgot your name.
It's Ethan.
Ethan, yeah, I'll make a note of that and I can make that happen for you.
Thank
No
you.
worries. Yeah, you betcha.
I guess we.
Question, have the final exam schedule's been released yet?
Not quite yet, but we're pretty sure it's gonna be this room Monday, 8 to 10 p.m. It's been a long standing, like 20-year tradition, it turns out.
Sweet, thank you very much.
Ethan Johnson, right?
Yes.
Gotcha.
And is, definitely like a specific time, or is it just as long as I put that day, I can choose any time?
Yeah, it is open for you to select the time.
Okay.
What happens is I'm gonna send an email out to the Idaho Falls Testing Center first. And that gets the exam put into their system.
Okay.
And then I send you a direct email, probably through Moodle, so you'll see it on the ISU email address as well. Showing you the link to the calendar where you schedule it yourself.
Thank you.
Yep, absolutely.
My final exam is gonna be.
It's gonna be on a Monday, it looks like.
On Monday.
It's gonna be a Monday, yeah,
So
and
it's in. Next week. Next week.
let's see.
Yeah. Okay.
Yep, looks like it's gonna be the 5th.